Okay, we are going through the example of spot speed data. Okay, so after you collect the data, you have to divide the values into what? Intervals or groups. Okay, and then you can prepare a table like this. Okay, so the first two columns are the intervals which you have here. The third column is what? Average of the interval. Okay, the fourth column is number of vehicles which is observed. The next column, percentage in each group, and the next one, cumulative percentage which you just add up. Okay, and what are the last two columns? Number of vehicles into which is speed? Average. Okay, then using this data we plotted these two graphs, right? So in the first graph, what we have on the x-axis? Middle speed. On the y-axis, the frequency. Okay, next one, maximum on the x-axis, and what on the y-axis? Cumulative frequency. Yes. Then we calculated some values for this data. Okay, actually we divided the values into two types. We divided the statistics into two types. What were those? Central tendency, which tell you about the center of the data, and the other one, dispersion, which tell you about the variation from the center. Okay, which one we have finished? Central tendency has been finished. Okay, what did we calculate in central tendency? Mean? No. Yeah, mean weighted average. What else? No. Standard deviation is in dispersion. Mode. What else? Pace. Median. Okay, we're calling median as a percentile. Okay. Yeah. So we're calling median as a percentile? Yeah. Okay, that's good. Okay. We calculated one parameter for dispersion as well, that was standard deviation. We calculated standard deviation. The standard deviation is not part of central tendency, it is part of dispersion. You are taking difference, right? You are taking difference. If you look at the equation, you are taking a difference. Okay, so it's not central tendency. Okay, so we started with dispersion. We only calculated one parameter of dispersion. Now we'll calculate the other parameters. So yesterday we found pace. You can see these are the same graphs. I will go to that graph which is bigger, this one. Okay, so we found pace in the last lecture. Okay, so it's a range of 10 miles per hour, which is where? In the middle. It's usually around the middle. Okay, now we want to know what percentage of drivers are driving in the range of pace. Now what is the range of pace? It is between 42.5 and 52.5. Okay, the pace which we found yesterday, you can see how did we find it, but we found it from the first graph. Okay, and it is between 42.5 and 52.5. Okay, so we want to know what percentage of drivers are driving between 42.5 to 52.5. We want to know the exact percentage. Clear? I will use the second graph now. For the pace, I use which one? First or second? First. To find the percentage, I will use which one now? Second. Because it's cumulative. So I start with 52.5. Now where is the speed? Which axis? The x-axis. Okay, the x-axis has the speed. So I will find 52.5 from the x-axis. It will be somewhere here. Okay, they drop the line from the top because it's on the same page, same scale. Okay, but 52.5 will be here, right? Okay, so from 52.5 you go to the curve and find out the percentage. That percentage is 77%. Okay, then you find the percentage for 42.5, same process. So from 42.5 you will go up and find out the percentage. Got it? Okay, and this percentage is 16%. Clear? Pace has two values, right? Upper limit, lower limit. I found the percentage for upper limit and I found the percentage for lower limit. Okay. Now this 16%, for example, means what? These are percentiles, right? These are percentiles, cumulative. Okay, so 16% means what? 16% drivers are up to 42.5.
Less than 40. Less than 40.
Up to 42.5. Up to.
Yes. Yes.
You mean up to? No, no.
No, I mean.
Yeah.
Yeah.
Equal or less. Equal or less. Okay? And 77% drivers are equal or less 52.5. Okay? So I know equal or less for 52.5 and I know equal or less for 42.5. How much between them? You take the difference. Okay? From 0 to 52.5, 77%. Up to, right? And from 0 to 42.5, 16%. So how many between them? You take the difference. You didn't get it.
No, okay.
Okay? Why you think so?
No, I can see from
Any question? Is it clear? Is it clear? Huh? Okay. The next measure of dispersion is, so you do 77 minus 16, it will give you 61%, which is the number of drivers in the pace range. Okay, now we have the percentiles, 85th and 15th percentile. From which graph I will find out the percentiles? First or second? Second. All percentiles are from second. Which percentile I am looking for? 85 and 50. Yesterday we found median, right? It was the 50th percentile, 50. We follow the same procedure. So if I want 15th percentile, so I start from which axis? Y axis. I look for what? 15. I draw the line and find out the speed at 15th percentile. It's 42.4. Okay. Then same thing for 85, right? I go y-axis 85% to the graph, down you find the speed. The speed is your 85th percentile. Okay? Clear? Clear? Okay. Then you can take the difference between them to find out. You can take the difference between them. Okay, basically. Okay. Now, why are we taking that 15th and the 85th percentile? They say the actual variation in the data is in between these two values. The normal variation of the data is in between 15th and 85th percentile. Whoever is less than 15th percentile and whoever is more than 85th percentile is not within the normal variation. He is abnormal, he is mad. Okay, it's just here because of Formula 1. Alright? There. Okay? So you want to know the normal range of data is between 85th and 15th percentile. Okay? Now you can see this range in this case is how much? 54.7 and 42.4, right? If you take the difference, it will be around 12 miles per hour, right? It will be around 42 and 54, around 12 miles per hour, right? If you collect some data, and for your data, this difference is 20 miles per hour. No, it's not abnormal. This is the normal data, but your normal data is very wide. Now you get the point. Here, the normal range is between 42 point something to 54 point something, right? The normal range. Okay? So this is not so big. Only 10 miles per hour difference in the normal range. Okay? But if you take the difference between these two values and you get a difference of 20 miles per hour or 30 miles per hour, that means what? Your normal data is even wide. The variation in your normal data is even more than this. Get it? Even normally the drivers are driving at very extreme values.
How will you know the number?
The 85th and 15th is a normal range. Okay? If this range is getting bigger, that means variation in the normal data is increasing. Okay? No matter how you collect data, there will always be some people who are at the extreme, right? Some values which are extreme. There will always be, right? So if you consider the extreme values, every data will look the same. In every data you will find a car which is going at 10 miles per hour and which is going at 200 miles per hour. Okay? So we exclude these values. The extreme values, we exclude them. What is the normal range of the data? Between 85th and 15th percentile. Okay? You want to see the variation in the data? Look at the difference between these two values. If this difference is less, that means the normal data is very close to each other. The normal range is very close to each other. Like here, it's only 12 miles per hour. If the difference is getting bigger, that means the normal data is getting more variation. Okay? Clear? Any questions? Okay. One more use of these percentiles is to calculate the standard deviation. We looked at one equation to calculate the standard deviation yesterday, right? Okay. This is another equation to calculate the standard deviation. Now you know both the values, right? Can you tell me the standard deviation? Huh? What did we do? 6.15. And how much was it?
1/4.
It was?
1/4.
This is 1/4. How much was it from the other equation? 6.1, right? It was 6.0 something, we made it 6.1, right? I think so. Anyway. But you can see the values are very close. Whether you calculate from that equation or this one, the values are very close. This one is easy, right? That one was difficult. We made it easy because it was already, the values were already done in the table. Right? So that one, this one is easier. Right? So which one do you prefer? This one. Right? You know there's a trick, right? No, you will prefer that one. Seriously. Okay? The previous equation. With the square root and the difference and everything. Okay? That is more accurate. Why that is more accurate? Because it deals with every group. Here you just took two values. Okay? So that's why they call it estimated standard deviation. You don't call it actual. That one is actual. This one is just an idea. Okay, clear? Okay, now we have calculated or we have found three measures of dispersion. Three. Can you remind me? Three measures of dispersion. Dispersion. What's all three of them today? Tell me. Standard deviation,
Percentile.
which percentile? 85th and 15th percentile, and it was related to pace. Pace is not dispersion. What did we find about pace today? We found the values of pace yesterday, right? What did we find about pace today? The percentage of drivers in the pace. Okay. So these are measures of dispersion. The standard deviation, whether you find it like that or like this, both of them measure of dispersion. Okay. These two percentiles are measures of dispersion, and the percentage of drivers in the pace is also measure of dispersion. Okay. Now, if the standard deviation is bigger, so instead of 6 I get 12. Variation is increasing or decreasing? If the standard deviation increases, variation is increasing or decreasing? Huh? Increasing. Okay, because standard deviation is the difference from the mean. So if the difference is more, that means the variation is more. The data is far from the mean. Okay, I am taking difference from the mean, right? So if difference is higher, that means the variation is more. Okay. Percentage of drivers in the pace, we found it to be around 60% for this data. Okay. So for some other data, let's say if it is 80%. So if the percentage is increasing, the variation is increasing or decreasing? Huh? Increasing? Yes? Because what? Where is space? Where is space? Where is space? In the graph, where is it? In the middle. So if the percentage of drivers in the pace is increasing, that means percentage of drivers in the middle is increasing, right? More people are in the middle. So variation is? Yes. Got it? Clear? More people, middle is where? Center, right? So if more people are in the center, variation is less. Clear? Okay. And the third one was the difference between 15th and 85th percentile. If the difference between, I think already mentioned, if the difference is increasing, that means the variation is increasing. Okay. The normal data is getting bigger and bigger. Here it was 12. But if it is 20 or 30 miles per hour, that means this data is wider. It has more variation. Clear? Okay. The standard deviation increases, variation decreases. Percentage of drivers in the pace increases, variation decreases. Okay. Difference between the 15 and 85 percentile increases, variation increases. Clear? Okay. Okay. I mentioned something about mode yesterday. That mode can be anywhere, right? Mode can be in the middle, it can be on the lower side, it can be on the higher side. Okay. But for speed data, it is usually where? In the center. For speed data, not for all data. Okay. For speed data, it is usually in the center. Okay. This is one of the characteristics of normal data. We call it normal data. Okay. A data which has maximum percentages in the middle. We call it the normal data. Okay. And according to scientists and data engineers and scientists, real world data, if it has enough values and no big mistakes, then it should be normal. Real world data, if you collected enough values and you did not make any big mistake in collecting them, then your data should be normal. So if you collected the speed data properly and in enough amount, then your data should be normal. And the normal data, the mode will be in the middle. Clear? Okay. So and obviously when the mode is in the middle, the shape of the graph will be like this, right? You can see the peak is in the middle. Okay. How many peaks we have? One peak. Okay. Yes, one peak. So where the peak is in the middle and we have only one peak, the data does not go up and down, it just goes up and then comes down. One peak only. Okay, we call it the bell-shaped curve. We call it what? Bell-shaped. So our normal data will produce a bell-shaped curve. Okay, which we have. Any data which is normal, you can write it with this expression. This expression, which you see in the second point, is saying X is a normal data. They call it normal distribution. Normal data or normal distribution. So X is a normal distribution data with first number as its mean and the second number is its variance. Okay? This expression is saying X is a normal distribution data with a mean of 40 and a variance of 25. Okay? Now what is variance? It is the square of standard deviation. My God, you guys know very well everything, right? It should come in the exam as well. Okay, clear? So if you see something written like this, it means we are saying something about normal distribution. Clear? Now you can see they are using the same notation in the last line. Okay, now what are they saying? What follows normal distribution? The mean is 0 and variance is 1. Okay, and what is following normal distribution? Z. Z is following normal distribution and it has a mean of 0 and the variance of 1. Now this specific data is a special type of data. We call it standard normal, not just normal. We call it standard normal. Okay? Because the mean is 0 and the variance is 1. So only the normal data which has mean of 0 and variance of 1 is called standard normal, not anything else. Clear? Huh? It is? Oh, I don't know. Okay. Clear? But whenever it happens, we call it what? Standard normal. Whenever you get mean of 0, it's not a problem, it's not a matter of how. You collected the data, you calculate the mean, it can out to be 0. What can be? It's normal distribution, yes. So mean of 0 means what? Half of the data is negative and half of the data is positive. Okay? So any data which is normal, mean of 0, variance of 1, we call it standard normal. And the notation for it is also fixed, Z. Use the letter Z for standard normal. Clear? Okay. Now since Z is standard, okay, so for Z, if somebody tells me my data has Z distribution, so you remember we calculated the percentile and mean and median and you are using the graphs, right? If somebody says Z, I don't need a graph, I already have a graph. Actually I have a table. Okay, so I don't even have to go to the graph and plot the lines and see it. No. The standard normal has a table. Okay, so from that table you go there and you take whatever percentile and median and mode, whatever you need, you can get it from the table. Okay, So having Z distribution makes my life easy. Okay? Easier, huh?
No, but we can convert.
We can convert, yes. So the equation which you see on the slide is for conversion. My data does not follow normal distribution, so my life is difficult. But I want to make it easy. So we do the conversion. Okay? Now this is converting what? This is converting x to z. So take all values of x, which is your data, and convert them into z. Now what is mu and what is sigma? Mu is the mean of your data and sigma is the standard deviation of your data. Okay? So if you have a data which is normal, it is not standard normal, but it is normal. Got it? You cannot convert any data into that. Okay? It must be a bell-shaped curve. So you already know that there is mode and the mode is in the middle and there is only one peak, it is making bell shape. Yeah, fine. But the mean is not 0 and the variance is not 1. So it is normal, but it's not standard normal. Now I want to standardize it. Okay, we call it standardization because we are now standardizing it to Z, right? Z is standard, right? Z is standard normal. I have just normal. So now I am standardizing it to Z. Okay, so you find out the mean of your data, you find out the standard deviation of data. You already have done it for our data. You have the equations, and then you convert all the x values to z values. What's the benefit? Now I don't need any plots. I don't need any graphs. I'll go to the z table and find out whatever I need. Clear? Clear? Okay. Whenever you are collecting data, there are two things which are very important. One is accuracy, the other one is precision, right? Okay. If accuracy is high, what will be low? If accuracy is high, what will be low? Huh? It will be low. Nothing will be low. Huh? No. Error will be low, right? Low error means high precision, right? Oh, sorry, high accuracy. Huh? Clear? Okay. The E is called the standard error of the data. So if accuracy is high, E will be there. There. Okay. What is S standard deviation? What is N number of values? So if you want to calculate the standard error of your data, have a standard deviation, and obviously you have the number of values as well. You can calculate standard error. Clear? Okay. Now, we said our data is what? No. In the previous slide, what did I say? Our data is what? Normal, right? Normal. For normal distribution, there is a theorem. We call it the central limit theorem. Okay? It only applies to normal distribution. Central limit theorem only applies to normal distribution. Okay? What does it say? Central limit theorem says if you are in the middle of the data, meaning you are at the mean value, you are in the center of the data, you are in the center of the graph. Okay? From this center, do 1.96e plus. So if your center is 20, for example, then 20 plus 1.96e, this e. Okay? And then do minus 1.96e. So you will have two values, right? One with plus and one with minus. These two values will cover 95% of data. Okay? These two values with plus 1.96e and minus 1.96e will cover 95% of data. So 95, if you are talking about speed data, so 95% of drivers are driving in these two, between these two values of the speed. Got it? Clear? Okay. another extension of central limit theorem, same theorem, but instead of 1.96e, they are saying now do plus minus 3 times e. So mean plus 3e and minus 3e. Again, you will have two values, right? Okay. These values will cover how much data? 99.7%. Okay. Clear? So if somebody did this plus and minus and he gave you two values, right? He gave you two values. For example, the lowest value is, or the value with the minus is 30 kilometers per hour, and when you do the plus, you get 70 kilometers per hour. Okay? You did 3 times e minus and 3 times e plus, you got 30 and 70. Okay? How much data is between them? How much data is between these two values? 99.7%, right? Okay. So you are 99.7% sure that any driver I see is in this value, right? Is between these two values, right? You are 99.7% sure, right? And if I do the first one, I am how much sure? 95% sure. Okay. So this is why we call it the confidence interval. These values which are coming from the theorem, we call it the confidence interval. In other words, precision. This is precision, right? How precise I am about my value. How sure about I am about my value. Okay? So in the first case, you are 95% sure. So you are 95% precise. There is 5% chance that you can be wrong, right? And the second case, there is how much chance? 0.3%. Clear? Okay. Now, can we find out the 95% interval for our data? Okay. We found the mean and the standard deviation yesterday, right? Okay. What was the standard deviation? It was 6.1, right? Okay, and the number of values? 368. Can you give me E? Abdullah Muhammad, Abdul Razak Badr, Ali Hussain. Which one? Mariam Shaki. Which one is Mariam Shaki? You are Nura. Everybody is there. Very good. Yes, how much? Okay. Can you give me this value now? I only need the mean then, right? How much was the mean? How much was the mean of my data? 14. Just write X bar, huh? 48.2 miles per hour. Okay, can you give me the confidence interval then? This value, mean plus 1.960. What can you give me this value? It's written, huh? How much is it? 48.8. Oh. So we have 48.2 plus 1.96 into 0.32. 48.8 and 47.9. Okay, these are all the speeds, miles per hour. What? 0.5? 0.5, 6?
5, 7, 6.
Happy? Okay. So this value will be called as, or this interval will be called as confidence interval. And how much is the level of confidence here? How much is the precision level? No. You calculate for 95% data, right? So my confidence level is 95%. Precision level, confidence level is 95. Clear? Any questions? Okay. We did it. Okay. Sample size, something very important for your term project data. Okay. For the second part of the term project. And this is basically where we have to, what we were waiting for. Okay. So for 95% data, we are doing plus minus this, right? 1.96 E. For 95% precision, we are doing plus minus 1.96 E. From what? From the mean. Okay. So let's say mean is the value I want, right? Mean is the value I want. In the end, you would do what? You take mean, right? Okay. You take the whole data, but in the end, you will take what from the data? The mean. The mean is the value I want, right? Okay. Now, how much plus minus you are willing to go in the data? Plus minus 1.96 E, right? So from the mean, I am willing to have an error of this much plus and minus. I am looking for the value of mean. And in this mean, with 95% confidence or 95% precision, I can do plus 1.96 E and minus 1.96 E, right? So mean is the value, actual value, and in this actual value, I can have, or I am willing to have an error of plus 1.96 E and minus 1.96. So we call it my error. Tolerance level. We call it the tolerance level. Error you are tolerating in your mean. Okay, in your data. And we know E equals to what? S upon root of n, right? E equals S upon root of n. Okay. So a small e tolerance level equals to 1.96 capital E, where capital E equals to S upon root of n. So n equals to what? N in terms of small e. The small e equals 1.96 S upon root of n. So n equals this. Clear? Okay. If you increase the precision level to 3 times e, so you are now increasing the level to 99.7%. So this will become your small e. So small e equals to 3 times S upon root of n. So n equals to what? Clear? Okay. So to calculate the number of samples for my data, what are the things I need? To calculate n, what do I need? Tell me now. You need the tolerance, meaning e, small e. You need to set the tolerance now. Okay, for your term projects, I gave it to you in the guidelines. I think it's 2. What else you need? Standard deviation. And but you need one more thing, right? How many equations you see here? 2, right? I see 2 equations, right? So I need to decide which one to use. So you need the confidence level as well. You need 3 things. Confidence level, you will select the equation. You need E, you will set it. Okay? For the project I gave it to you. And you need what? Third? Percent. Okay? So for the project I gave you the tolerance level, I gave you the confidence level. Now from where will you get the standard deviation? From? Where is the data? When did you collect it? Task 1. Okay, so now your first step is find out how many values you need. Okay, some of you do the other way around. Huh? Yeah, let's go to the road. We'll have fun. Doctor, we collected 100 values. Now what do we do with it? No, do this first. Okay, so you know how many values you need. Clear? Okay, so just to get it going, the concept which we have learned. How many speeds must be collected to determine the true mean speed of the underlying distribution to be within plus minus 1 mile per hour? What is this plus minus? The tolerance, that small e, right? B plus minus this, right? Okay, with 95% confidence. Okay, and how the results will change if the tolerance is changed to 0.5 and the confidence is changed to 99.7%. So they are asking us to use both equations. Okay. Okay, first of all, I'll put the equations over here. What happened? Okay, we will make a table now. Okay, so we are changing the confidence interval. So 95% confidence and 99.7% confidence. And we are changing the tolerance. Okay, so tolerance is plus minus 1 and it is plus minus 0.5. Give me the values for each case. We're using both combinations, huh? Huh? Yeah, for the first row you will use the first equation, 3.84 s square. Now what is missing? S is missing. Okay, do we have any previous data? No. Okay, here we don't have. Here we don't have. Okay, so in those cases they are saying take it 5. In those cases take it 5. Take it 5. $96. Which one? 192. Huh? So? Huh? 900. Sorry? 0.5. What?
Because should be 384.
No, the maximum is here. That I know.
But the first one, 192.
Is how much?
384.
384, okay. You were telling me values in half, huh? Okay, clear? Any questions? Now, if you increase the confidence level from 95 to 99.7, the values increase, right? The values are increasing because we want more precision, right? We need more values. Okay, we need more values. Okay? And what about the tolerance? What happens to the values when I decrease the tolerance? The values are increasing because less tolerance means what? More accuracy. So if you want more accuracy, more precision, you get more values. Okay? So now you have already seen two things here. A standard deviation, if it is not given and you don't have any previous data, you take how much? 5. If it is not given, but if you have previous data, like your project, you will calculate it from there and apply it here, no problem. Clear? Okay? There could be a third step, not the second step. So for example, you take 384. You go and collect 384 values. Okay? Now you can recheck. Because with 384 values, you can recalculate the standard deviation, right? It will be the actual standard deviation. 5 was what? Assumed, right? And in your term projects, the standard deviation is for some other data, not the data of the sample, right? So you can recalculate standard deviation and check from the same equation, do you have enough values? So for example, you collected 384 values, right? Now you recalculate the standard deviation from those values and put it in the equation again and see how many samples are you getting. Now let's say the equation gives you 300. Any problem? Because you already have 384 values, right? So no problem. If the equation gives you 400, then problem, right? Now how many values I will collect? 16 more because 384 are already there. Okay, clear? Okay, so whenever you are dealing with standard deviation, you get it from somewhere else or assume it, you can perform this check. But in your projects, you don't have to do this check. I'm just telling you in real life how does it work. Clear? Okay, thank you.